Hello, welcome to the channel. In previous videos, we have started discussing KSET January 2024 question paper. Already 3 videos have come on this question paper. In first 2 videos, inorganic chemistry as well as interdisciplinary topics have been discussed. And in the previous video, organic questions. So first 15 questions out of total 30 organic questions, first 15 questions have been discussed. So now in this video, we shall take up the remaining organic questions. Before starting questions, if you are looking for chapter wise as well as topic wise sorted KSET previous year question papers, you can have a look at these books, Inorganic Chemistry as well as Physical Chemistry, where all previous appeared KSET questions have been sorted, and then detailed solutions for all those questions it has been given in these books. So to order your copies, you can just give a WhatsApp message to the number. First question, it is about selenium dioxide reagent. So like selenium dioxide, it is a oxidizing reagent. So how it oxidizes this particular compound, that is the question. First thing that we should know about selenium dioxide is that SeO2, it oxidizes allylic carbon. So if you look at this particular structure, so double bond you have here, so like with respect to this double bond, this is alpha position or this is allylic position. So this is one more allylic position, this is one more allylic position, and of course here hydrogen is present, and that's how allylic carbon it is not available on this side. So now this is available, and here it is available. So out of these three positions, where the oxidation happens, that is the question. For that we should know these facts also, that selenium dioxide oxidation, it happens at more substituted side. So now if you consider these two carbon atoms, so this side we have two substitutions, this side just one substitution. So this side it is actually more substituted one. So this side we should expect oxidation. Between these two, this is a carbon atom which is involved in the ring, whereas this is not. Selenium dioxide, it prefers to oxidize this position. So that is the position where the ring is present. So that's how OH group it is introduced here, and the correct answer for this question, it will be option B. Option B, where the allylic position, it is taking up allylic ring position, that is taking up OH group, or it is undergoing oxidation. So option B is the answer for this. The next question, it is about hydroboration oxidation. 9-BBN, it is a reagent which stands for 9-bora tricyclo-331 non-N. Simply, it is a hydroboration agent. So as I mentioned earlier, first they have considered hydroboration, and then in the second step it is oxidation. So now if you consider hydroboration oxidation of this particular structure, so what will be the product? So hydroboration, so this structure it is simply represented like this. So the important thing is that hydrogen as well as this boron part, it will be added across this double bond, and it will be actually happening in cis manner. And the very important thing is that where this hydrogen goes, whether it is in accordance with Markovnikov's rule or it is anti-Markovnikov's. So in this case, this reagent it is being bulky, so this boron part always it occupies less steric side. So now if you consider here, so here there is substitutions, therefore this boron part it will come to the other side, less substituted side, and hydrogen it takes up this position as I have shown here. Next step, it is very simple, H2O to NaOH, it will just remove this part and it will introduce OH instead, right? So the product it should be this, and the correct answer I think it is given here, option D. In all other things, in all other questions, they have retained the double bond as it is, but in hydroboration oxidation, the double bond it is converted to single bond, and here one more carbon atom is there, and that's how it is. This option D is the correct answer for the question. The next question, it is based on something called as ompolum. So to answer this question, first thing is that we should know what is ompolum. So ompolum, it is chemical modification of functional group to reverse the polarity. In a regular way, a functional group it is having polarity in one particular way. If you are thinking of reversing that, in that case we can call such a species as ompolum. So now for example, if you consider carbonyl functionality, the regular polarity it is like, so this oxygen it will be having delta minus charge and this will be having delta plus charge. Or for the other possible structure, say if you have this kind of structure, say if you have minus charge here, so in that case also polarity it will not be reversed, because so this it can undergo delocalization like this, and because of that we will get in the regular way itself. So this bond, if it turns to be single bond, this will be plus and this will be double bond. So the thing is that here the carbonyl carbon it will be having positive charge and the oxygen it will be having negative charge. That is the routine polarity of carbonyl, right? So now if you look at the options A and B, so in that case carbonyl it maintains this kind of minus charge stabilization, and the regular polarity it is maintained. So this one it will be having like carbonyl in both the structure. So the carbonyl it will be having the regular polarity itself. But if you look at the C structure, what they have done is, so they have done some kind of polarity reversal, and the carbonyl carbon it is taking up minus charge. So that's how this is the ompolung, where the polarity has been reversed. If you look at the option D, this is regular way. This species it is stabilized by hyperconjugation. So say if you simply start with a species where some halogen atom is attached, and if it is removed as X minus, you will get this, and that's how this is in this molecule the polarity is in regular way itself. Only here the polarity has been reversed. So therefore this can be called as ompolung, and this is the answer for the question, option C. The next question it is from retrosynthesis. So in retrosynthesis, to design a molecule, it is considered that the molecule whatever is to be designed, so that will be broken into pieces or fragments, and based on those fragments, like whatever starting materials are to be used to synthesize the molecule, that will be found out. That is retrosynthesis. So now here this bond they have shown that it is considered for breaking. So very important thing or very simple thing is that among the four options, in two options they say it is CX disconnection and CC disconnection. So this cannot be CX disconnection. So therefore readily you can discard these two options. These two, they are not possible because here they are breaking CC. Now the next thing that we should decide whether this is 1,1 CC disconnection or 1,2 CC disconnection. So if you have some entry into retrosynthesis, easily this can be answered. So now if you consider breaking of this particular bond, the species in retrosynthesis that can be considered for the formation of the molecule, it will be like this. This species it will be having minus charge. So like the starting material corresponding to this species, it will be a Grignard reagent. So Grignard reagent, if you consider it is masked carbon ion, and here you can think of having minus charge. And carbonyl functionality, if you can have a species with positive charge, right? And this, when it is attacked by this Grignard reagent, it takes up this particular structure carbonyl. So that's how this is the retrosynthetic approach to synthesize this molecule. Now what is this, whether it is 1,1 disconnection approach or 1,2 disconnection approach? So like if you consider this bond breaking, the functional groups, they are immediately present at the first position itself. If you consider this bond for breaking, so here you have functional group immediately at next position, and here also you have the functional group immediately at the next position itself. So that's how this is considered to be 1,1 disconnection approach. 1,2 CC disconnection approach, usually it will happen if one of the reactant it is epoxide. So in that case the functional group it is little bit away, so it will be 2 carbon atom away, or say at a distance of 2. So that's how it will be considered as 1,2 disconnection, but this is 1,1 disconnection approach. The next question it is about prochirality. They have given a statement: if a prochiral ketone it was converted to enantioselectively to a chiral alcohol with a Grignard reagent under asymmetric conditions, which of the following statements would be false? So whatever statement they have given, so that can be represented in the form of equation. We have a prochiral ketone. So prochiral ketone means the attached groups it should be different, that is treated with Grignard reagent to produce a asymmetric alcohol. This will be asymmetric alcohol because all the 4 groups they are different, and this carbon atom it will be chiral carbon atom, and that's how this will be a asymmetric alcohol. So now regarding this particular reaction, they have given 4 statements, and among these statements which is wrong or which is false, that is to be identified. We can have a look at each statement. First one, the reaction center is sp2 hybridized carbon atom. Yes, this you can find that here sp2 hybridized carbon atom is present, and that's how, yes, first statement it is absolutely right. Second statement, nucleophilic attack by the Grignard reagent will be selective for one anisotropic phase over the other. Yes, this is also true. So when you have prochiral phase, the attack either from this side or from the other side, that will be preferred if, say, like only one product it is formed, as they are mentioning in the stem of the statement. So if this has to happen, only one particular product, if it has to be major product, so in that case, the nucleophilic attack, it should be preferred from one of the anisotropic phase. The phase that you are seeing now, that is one phase, and the other phase means the nucleophile, it will attack from the other side, rare side. So the statement 2, it is also correct. C, a chiral product would be obtained regardless of which Grignard reagent it is used. So this statement, you should observe it carefully. Now we have X and Y and R here. So if this X, Y, R, they are different, then only you can expect that the product whichever is formed, it will be chiral. Say now this R group, it is, if it is same as that of X or Y, in that case this particular carbon atom, it will not be chiral. Say for example this R group, that is also Y. So in that case this molecule, it will not be chiral molecule, and chiral alcohol, it cannot be obtained. So therefore option C, it is wrong. Whether we get a chiral product or not, that depends on the Grignard reagent that we are using. So if the Grignard reagent, as I mentioned earlier, the R group, if it is same as that of X or Y, in that case chiral alcohol, it will not be obtained. So therefore option C, it is wrong, and that should be the answer. They have asked us to identify the false statement or wrong statement. Option C being false, that is the answer. We can have a look at option D also. The prochiral ketone has different groups linked to the carbonyl group. Yes, then only it can be called as prochiral. If these two groups, they are same, in that case both the phases, they will be same, and the molecule, it cannot be called as prochiral. So for the carbonyl to be prochiral, this X and Y, it should be different. So option D also correct statement. So that's how only option C is false statement, and that is the answer for the question. The next question, it is again from stereochemistry, a little bit of higher level of stereochemistry. They have given a reaction, say where a carbonyl compound with one more carbon center, which is having three different attached groups, that is, this is a symmetric center readily, and that is treated with this reagent, and now product is also given. So like now the question is, according to which model this particular product, it can be predicted. See, for these kind of stereochemistry predictions, we have different models like Cram's model, Cram's chelation model, Felkin ion model, and all. So you should have sound knowledge of all those models, then only it can be answered. Otherwise it goes very difficult to answer this question. So the first thing that we can do here is that this is not Cram's chelation model. This option we can discard, because Cram's chelation model, it will be applied when reagents like zinc borohydride or say the metals like zinc, they are used. So they are capable of coordinating, or they are capable of forming chelation with groups such as OCH3 or nitrogen or sulfur compounds. That will happen, and that's how this cannot be Cram's chelation model, because we do not have suitable metal here. This can be discarded. Now among the other three, which is the correct answer, to decide that we may have to work out that. So I'll just show how we can work out with Cram's model and Felkin model, and based on that how we can decide the answer, that we shall see now. So according to Cram's model, this molecule, it is visualized say from this side, and if we are visualizing it from this side, this carbonyl and pH, they are appearing on the front carbon atom, as you can see here. And in Cram's model, among these three groups, they are categorized as small, medium, and large group. Large group, it is considered to be eclipsed with the R group of the carbonyl. R group of carbonyl is pH here, so that will be eclipsed. OCH3 group, it is larger group, and that will be in eclipsing orientation in the reactive site, or in the reactive conformation of the molecule. And then the nucleophile, so in this ET Li, ET minus, that will be the nucleophile, that will be attacking the carbonyl from the side of smaller group. Between now ET and pH, this ET, it is smaller, so therefore attack, it will happen from this ET side, this ET side, right? So now the resultant, so this ET, it is coming along with this ET, so therefore this ET, they'll be in eclipse conformation. And next what we can think is that this double bond O, it will be converted to OH, and that will be going away. So that's how this OH, it takes up this position, pH as it is. So on front carbon atom, front and back carbon atoms, you may have to observe them very carefully, pH, ET, OH, right? Whereas on rare carbon atom, we need not worry because this orientation, it will not change on rare carbon atom. So just whatever they have given here on the rare carbon atom, the order we can just have a look at ET, PH, OCH3. If we move in clockwise direction, it is ET, PH, OCH3. Just we can retain that. So here ET, it will be in eclipse with the new ET. So ET, and then on rare carbon atom PH, OCH3, that is followed. ET, PH, OCH3, that is followed. So that has been kept as it is. So now to get this particular orientation into the given orientation in staggered conformation, we may have to move the rare carbon atom, this carbon atom OCH3, ET, PH groups, that we may have to move in such a way that this OCH3 group, it should take up this position, right? So that has been done, and the order it should follow just like OCH3 and then ET on PH, OCH3, ET, PH, right? So now if you compare these two, so OCH3, this side they have OH and this side they have ET, but according to Cram's model, the product, it should be like this. ET, it should be here, and OH, it should be this. So that's how this product, it is not predicted according to Cram's model. To do the same thing, the other model, it is Felkin model. So in Felkin model, again, we are visualizing the molecule from this end itself. But the thing is that here, the R group of carbonyl, that is pH group here, it will not be kept in eclipsed orientation, but that will be kept away from, or kept at 90 degrees to this carbonyl and the R group. So that's how it is kept here. And now the nucleophile, again, it will attack from the small side. ET and PH, if you consider, so it is the smaller side. From this side, it will attack. So now the product, if you write, so this is new ET, it is taking up this position, and the carbonyl, it will be converted to OH, and this PH, it will be here. On the rare carbon atom, it is same, ET, PH, OCH3, as they have given, ET, PH, OCH3. Now again, same thing we have to do. We should consider the rotation of OCH3 or the rare carbon atom to get the OCH3 group to this position. So if we just do that, OCH3, it will come here. The order is OCH3, ET, PH if we move in clockwise direction, OCH3, ET, and PH if we move in clockwise direction, right? And now this can also be moved to get the proper orientation. Just if you think of moving this OCH3, ET, and PH, OH, ET, and PH, OH, ET, and PH, they'll be in this particular orientation. So now the given molecule or the given orientation, it matches with this. So that's how this is actually according to Felkin model. Of course, to understand this, if you have worked this kind of work with this kind of models, then only you can understand this. Otherwise, it goes a bit difficult to understand this. So the thing is that you should first understand what is Cram's model and how things are worked out in Cram's model, and same thing with the Felkin model. And if you have practice, then you can confidently do that. Yes, this is not Cram's model, but this is a Felkin model. Little bit difficult question. Next question, it is very simple one. Cope rearrangement, it involves which kind of sigmatropic shift? Cope rearrangement, it is just say you have 1, 2, 3, 4, 5, 5 dienes. They can undergo sigmatropic shift, or they can undergo pericyclic reaction to give in thermal conditions itself. So to give this kind of products. So now the question is which kind of sigmatropic rearrangement it is. So to decide this reaction to be which type of sigmatropic rearrangement, what we should consider is that we should consider the bond that is being broken. So the Haro moment, it can be shown like this. So here, this bond, it will be broken here, and the new bond, it will be formed between these two carbon atoms, and this double bond moves here. That is the movement of electrons. The bond being broken, it is this one, and the new bond formed, it is here. It has been shown. Now, when you consider this bond broken and say partial bond formed step, you should just count the number of carbon atoms that are available with the fragments. So 1, 2, 3. Here also it is 1, 2, 3. So that's how this is considered to be 3, 3 sigmatropic shift. And option C, 3, 3 sigmatropic shift, that is the answer. And of course, even if you know by the fact that Cope rearrangement, it is 3, 3 sigmatropic shift, you can directly answer this question. Next is a named reaction called as Barton reaction. Here things can be little confusing. Barton reaction, it is used to functionalize. So what is Barton reaction, that we shall have a look at. So when we have a molecule with the NO2 group, that molecule, when it is subjected to photochemical conditions, we can expect homolytic cleavage of this bond to form alkoxy radical here. This alkoxy radical, it will take up the delta hydrogen, because if it is delta hydrogen, stable 6-membered orientation, it will give access to this alkoxy radical to this hydrogen atom, delta hydrogen, so that will be abstracted and OH will be formed here, and later this NO dot whichever is removed, so that will attack back here to give this position or this product, right? So now they have asked Barton reaction is used to functionalize the product, it is this one. So now in the product, if you look at, this is alpha, this is beta, this is gamma. At gamma position, alcoholic functional group it will be present. So that's how Barton reaction, it is considered that it is to functionalize gamma position. But remember, it should not be confused with the delta hydrogen removal. The hydrogen whichever is removed, it is from delta position. This hydrogen you can call it as delta, right? So alpha, beta, gamma, delta carbon atom and delta hydrogen. But the functionalization with respect to the NOH group, oxime group form, it will be gamma position. So that's how Barton reaction, it is considered to be for functionalization of gamma position. Next, very simple question. It is again from pericyclic reaction. 4+2 cycloaddition reaction they have given, very well known cycloaddition reaction. But what is the product that they have asked, right? So now the thing is that in this reaction, the simple thing that happens is that if you just consider the things in this orientation itself, right, the thing that happens is, say this double bond, it can attack here, and this double bond, it will come here, this double bond, it will go here, and the product will be formed. This 4+2 cycloaddition, it can happen in two different ways. OCH3 group and this particular group, if you have it in this particular orientation, you get a product where 1 and 2 positions are substituted. OCH3 in the product, it will be substituted at 1 and the next position. But if you consider the orientation in this way, the OCH3 and the other functional group, CHO group, it will be, its position, it will be relatively different. Now, which is the possibility? That is the question. First thing is that this diene, it is subjected or it is substituted with OMe, electron donating group, which favors again the 4+2 cycloaddition. Dienophile, that is also substituted with the electron withdrawing group, so that also favors 4+2 cycloaddition. Now, among these, between these two, which cycloaddition it is preferred? So that can be simply decided simply by writing the electron movement, or say because of this electron donation due to OMe3, what are the charges developed that if you look at? So OCH3, you can consider it like, say OCH3, it will be donating its pair of electron here, and this pair, it will move here, and this will come here. So that's how it will be having minus charge. Similarly, here this double bond O, if you expand this double bond, it will move here, and that's how here you can expect positive charge, and O, it will take up minus charge as they have shown here. Always positive negative interaction it is favored. So in this particular orientation, whatever they have shown in that particular orientation itself, this negative positive interaction it is favored, and the product, that's how it will be this one, right? So if you consider the other way, so here the charges developed, it will be not favoring the 4+2 cycloaddition, because these two positions, they'll not be getting the opposite charge. So that's how in this particular orientation, minus charge and plus charge, they are in the proper orientation, the product, it will be this one. Next question, it is from heterocyclic chemistry. In fact, a very simple question. They have just asked about the bromination of indole, whether that bromination it happens at the second position or third position. That is the question, because in indole, the bromination, it will happen at this 5-membered ring itself, not at benzene ring. So if we just know that fact, then we can discard some of the options. But I think in this question, only one such condition is given. But here, so they have done bromination at both the rings. This is not possible. Bromination, electrophilic substitution. So like bromine being attached to the molecule, that is not possible. So therefore this option B and option C, readily it can be eliminated. So next we are just left with option A and D. So here the bromination has happened at second position, and here the bromination, it is at third position. So now if you consider both the possibilities, first if you consider the bromination at third position, so third position, it will leave a positive charge. You can just follow this. positive charge over nitrogen, and if you consider the electrophilic substitution at second position, you will get positive charge over nitrogen, but this positive charge, it will be later delocalized over benzene ring, which disrupts the aromaticity of the benzene ring. So that's how the electrophilic attack at the second position, it is not favored. Whereas here, if it happens, electrophilic aromatic character of benzene ring, it is not disrupted. Therefore, electrophilic substitution, it is preferred at the third position, and the corresponding answer that they have given is option A. Next one is also simple one from heterocyclic chemistry. So if isoquinoline, if it is treated with KMnO4, what will be the product? Of course, they could have given that it is alkaline KMnO4, but okay, we can understand that it is alkaline KMnO4 itself, because the product, it will be different with neutral KMnO4. But if you consider alkaline KMnO4, which is a most common reaction of isoquinoline, so what happens is that this being strong oxidizing agent, it cleaves the ring at these positions, and that's how you will get phthalic acid as one of the products. The other possibility is also that, so the ring, it can be cleaved here. If the ring, it is cleaved here, in that case pyridine 4,5-dicarboxylic acid, that will also be one of the product. But among the given options, we can find phthalic acid, so that's how option C, we can consider that the correct answer. Next one, it is about Zeravitinov method. And Zeravitinov method, it is used for what? That is the question. If you know Zeravitinov's method, this question, it can be answered very easily. So in Zeravitinov's method, the compound, any compound, it will be treated with methyl magnesium iodide reagent. Zeravitinov's reagent, it is methyl magnesium iodide. So when it is treated, when the compound, it is treated with the reagent, acidic hydrogens whatever are present, so they will be converted to methane. So here this particular hydrogen, it is acidic, CH3 minus, it will take up this H plus and it will form CH4, and later the volume of CH4 whatever is produced, that will be measured, and based on that, how many acidic hydrogens are present in the given molecule, that will be worked out, and that's how acidic hydrogens, or the active hydrogens, to be appropriate, it can be called as active hydrogens. So in Zeravitinov method, it is active hydrogens which are which are determined, and not OCH3 group of group or other things. 98 question, which of the following is reducing sugar? In fact, simple one, but because some different options they have given, it could be little confusing. One thing is that glucose, it is reducing sugar, we know that fact. So what is reducing sugar, that we should know. So reducing sugar or non-reducing sugar, it is based on some tests, and those tests, they make utilization of silver plus or copper 2 plus ions, and the carbohydrate, it will be undergoing oxidation by reducing this, and such a sugar which is capable of doing that, which is capable of say reducing Ag and copper 2 plus, that will be called as reducing sugar. So like, which are those tests, you can just comment that in the comment box. So two particular tests are there, one it makes use of Ag plus, and the other one it makes use of copper 2 plus. So like, which are those tests, you can just mention that in comment. Right now, the necessity condition is that if you have free aldehydic group in the open chain structure of the carbohydrate, then definitely that will be a reducing sugar. Or if you have cyclic hemiacetal functional group, that cyclic hemiacetal functional group, definitely that will be in equilibrium with cyclic aldehyde. So if this condition is followed, then such carbohydrates, they can be reducing. So now one thing is sure, that here C is definitely the answer. Confusing, it can be confusing because if you do not know about dihydroxyacetone and erythrulose nature and structure, so then there are chances that you can think that even these could be reducing sugars, and you may go with this option D. But no, these two, they are keto sugars, and in their open chain form, they'll not be having aldehydic structure. That's how these two, they'll not be reducing sugars. So you can just have a look at these two structures to make sure that in their acyclic form, they do not contain any aldehyde. So that's how option C is the correct answer for this. 99th question, predict lambda max of the following compound. Right, so seriously speaking, among the given options, all the four, they are wrong, but yet Grace Mars, it was not considered, or this question, it was not considered for Grace Mars. And but why they have done so, or like how they have calculated lambda max, really I do not know. for this prediction of lambda max, we follow some rules called as empirical rules called as Woodward-Fisher rules. So according to that rule, if you go, so this is a cissoid form. So this particular structure, whatever they have given, it is in fifth form, and the base value for this cis itself, it will be 253. Right? According to this table, we can go on doing some additions. So if we consider this particular moiety, so there is a ring residue or substitution here. Here also same thing. For that 10 it will be added. So somewhere around 263 nanometers we can expect. Right? And nothing else is there. No other additional conjugation or no other groups. So therefore the answer it should have been 263. And the given answer it is 227. Maybe the base value, I think they have considered it as 214, which is for actually transitoid system, but the given system being cissoid, the base value that we should consider is 253, and the answer it should have been 263. None of the options they are matching with. So I think this one they have given it based on the transitoid system, considering this to be transitoid system, and base value I think somewhere around 214 they have considered, and in that case it will come to not 227 exactly. 214 plus 10 means it would come somewhere around say it will be 224, right? So but the answer it should have been 263, but grace marks it was not awarded, and I don't know really on which rules they have asked this question. If we go with Woodward-Fisher rules, I would consider 263 to be the correct answer for this, which is not given here. The last question, again it is based on spectroscopy, very simple one. Number of 13 C NMR signals they have asked. So the easiest way or the trick to find out this is that if a molecule is given, if it is symmetric, just we should identify the symmetry. So here we have a plane of symmetry. That means this part of the molecule and this part of the molecule, they are the same. And one more symmetrical plane that we can consider here in this molecule, it is this. So if you just divide the molecule based on these symmetry elements, this molecule it is highly symmetric. Now once you identify the symmetries, later what you can do is you can just choose one of the part. Now say this part I can choose, and just I can count the number of carbon atoms, and that many signals we get. So here, like, this is not the proper way of numbering for nomenclature, just to count the number of carbon atoms, 1, 2, 3 and 4, right? So because of symmetry, all other groups or all other parts of the molecule, so they'll be giving you the signals at same position. So that's how the total number of signals in this molecule, it will be 4. Option B is the answer, right? So with that, all the organic questions it has been completed. So in this particular video, I have considered 15 questions. Previous 15 questions that has been considered in the other video, that also you can watch. So this KSET January 2024 paper, inorganic question paper, that has been inorganic portion of the question paper, it has been dealt in 2 more videos. You can also watch those videos. If you are new to channel, you can think of subscribing the channel for videos of this kind, and you can forward this to your friends and subscribe and follow the channel. Thank you for watching video. Thank you again.